So today we will start a discussion about nanoparticle or nanoclusters, which are magnetic nature. Uh, so when we talk about these magnetic clusters, so in general, any magnetic material, so mostly they will have a domain structure, right? So it could be in a single domain, in a multi-domain state. So like what is shown here on the left, and so different domain that can exist in a material, and then how do you know that these domains they exist? So when you measure the magnetization versus magnetic field, so you get a hysteresis loop. So this hysteresis loop actually tells you that you have, so your magnetic material is divided into uh, smaller domains, and within each domain your magnetic moment, that is all are aligned or pointing in the same direction. Okay, now let's now if we start to make it smaller, so we break this big bulk magnetic material which has lots of domains, and we break it up into smaller size. So what happens? So most likely it is going to be, I mean, either it can be in a multi-domain state, or it might go to a single domain state. Okay. So what actually is observed is your this single domain state is actually energetically favorable. Okay. So we can actually calculate these energies of different uh, like materials in multi-domain state or in a single domain state. One can do a very simple calculations, and we will just see how we do that. But what is happening is, like, when we decrease the size of a ferromagnetic particle, so when we are talking about these domains, so we are saying these are ferromagnetic particles. Okay, so there can be also other magnetic uh, ordering that can also exist, like antiferromagnetic or ferrimagnetic, right? So different magnetic structure that can exist, but mostly what is used are these ferromagnets that are actually used for lots of applications. And when you decrease the size, so they decrease, so the multi-domain state will reduce to a single domain state, and that is much more energetically favorable compared to this. So in a when you go to a smaller size, so your single domain state is energetically favorable compared to your multi-domain state. Now the question is there a change in the hysteresis due to that? Is it going to change or not? Yeah. Okay, uh, so what is done actually in this single domain state? So what you can do is you can represent this all the, so we have lots of spins which are pointing in the same direction. So this is on the right hand. Let me just draw that. Yeah. Okay, so here you see it's like a single domain state, right? And all the spins are pointing in the same direction, okay? And what you can do is you can represent it like a ferromagnetic particle with a large spin, okay? So you can approximate it something like that, just like a dipole where you have a big So this is something very similar to a big dipole that is formed here. And this spin here, you call it a super spin. Okay, so this you call here super spin, because the magnetic moment of these materials will be quite huge. Why? Now, if you consider, let's say, if you take one magnetic moment, so one magnetic moment, let's say the magnetic of one atom. So the magnetic moment due to that can be few mu Bohr, okay, Bohr magnetron, because mostly the magnetism is coming from the electron's spin, okay, and therefore the magnetic moment per atom will be typically of few mu Bohr. So due to few of the electrons, and therefore atomic magnetic moment will be very small, okay. But if you calculate now, if you take such like thousand number of such atoms, and all are oriented in the same direction, so in that case you get a magnetic moment which will be quite huge, because in this case all the tiny, let's say, all the tiny magnetic moments, atomic moments, are all aligned in the same direction, and then they add up, and the net magnetization of that ferromagnetic particle will be really huge. Okay, and that's why you this is why the name is, we call it a super spin. So now the question is how the corresponding hysteresis loop would look like. Okay, yeah. Before we go into this further, so what I want to show here is like how the this like under which condition this super paramagnetic particle, or let's say we do not know it is super paramagnetic right now, so with this single domain ferromagnetic particle, what we saw in the this case, the single domain ferromagnetic particle will be energetically favorable. So to do that we have to calculate the energy. Okay, so let's do that. Let me just add here. Okay, okay. Let me see if it is visible to you. Oh yeah, okay. Maybe I can increase a little bit. Yeah, okay. Okay, so let's calculate the energy of these single domain particles. So we have, let's say, so we say this is, we have two domains or four domains here actually. So here we have two domains, and here we have a single domain, right? So we can call this A, B, and C. So we want to calculate the energy in all the three cases. So a simple way of so what are the energy contribution? So magnetic energy contribution to the for the particles. So typically these energy contributions are, oh, sorry. So these are your magnetostatic energy, okay, or sometimes it is called also dipolar energy, or a volume energy, okay. So there is, this is one contribution, and another contribution is, your uh, domain wall energy, Okay, so when we create these domains, the moment we create these domains, so we have domain walls, right? So this is your domain walls. Since we are creating these domain walls, so it will cost some extra energy as well to the system. And so therefore you will have two different contributions, primary contribution to the domain, to the energy. So one is your magnetostatic energy, and the other is your domain wall energy. Now, how do we calculate that? This domain wall energy, or let's say the first, let's say the volume energy. So the volume energy we can calculate is using this equation. So minus half. So like what we have is HTM dV. Okay, so this is your you integrate over the whole volume of the material. Okay, and you get the volume energy, or the, let's say, the magnetostatic energy. And what is this HD? HD is normally is called as a demagnetizing field. So this demagnetizing field is always present in any ferromagnetic body. So if I take a ferromagnetic body, let's say in this elliptical form, so if I have a magnetization M, so it will always have a demagnetizing field which is in the opposite direction to the magnetization direction. So it is always will be present. So every ferromagnetic body is always associated with a demagnetizing field, and sometimes so it is always associated with the shape or the geometry. Okay, so typically you write your HD is like N into M. So it is proportional to M, and this N is a demagnetizing constant. Okay, so it will be always opposite to your magnetization direction. So minus N. So demagnetization factor or constant, you can call that. Okay, and this is always will be there for any ferromagnetic body. Okay, so if you take any ferromagnetic body with a magnetization M, so let's say and so it can be in rectangular form or cylindrical form or spherical form, doesn't matter, you will always have this demagnetizing field. But this value of n can be very difficult to calculate for different geometrical shapes. Okay, so for simplistic geometrical shapes, it is easy to calculate, but for arbitrary shapes, it is very difficult, and therefore, for spheres, basically this HD. So if I take a sphere, so HT will be typically, you say, like minus one third of M. So your value of N will be one third, and this is like the sphere is like, you can say it's mostly a isotropic distribution. So therefore, the demagnetizing field will be also isotropic, and you get one third for each direction of like x, y, z. So different Cartesian coordinates. So you get a one third contribution. So that's why you can. So this is how the demagnetizing field for a sphere would look like. Also, I mean, of course, for a cylinder it will be different. For a flat, like a plate like structure, it will be different. For disk it will be different. I mean, this HD value is different, and there are some already available calculations which shows what will be the HD value for different geometries. But for arbitrary shapes, this is very difficult to uh, calculate. And so, what is this HD actually is doing is, so let's say if I take a ferromagnetic body and I am applying a magnetic field HA. Okay, so this is my external field HA. But what will be the field that is, this is a ferromagnetic body M. Okay, with a magnetization M. So now, if there is no, let's say, there is no ferromagnetic body, it's just there is nothing there. Okay, so let's say there is nothing here. So your H, and I am applying a magnetic field HA. So my H will be equal to HA. But if I introduce now a ferromagnetic body here with magnetization M, then my H magnetic field H field will change because I have a demagnetizing field due to the ferromagnetic body. So I have the total magnetic field H will be this magnetic field will be HA plus HD. So now the actual magnetic field inside, so this HD field it exists inside, okay? So HA outside it is always the applied field, but this H, what we are calculating right now, is inside the ferromagnetic body. So this will be HA minus N into M. So the actual magnetic field inside your ferromagnet will decrease or will be less than your applied field due to this demagnetizing field. So that is what this demagnetizing field, that is what the role it plays. Okay. So inside the ferromagnetic body, the magnetic field will be reduced or changed due to this demagnetizing field. Uh, so now, then how do we calculate this energy? So as I said before, so energy will be equal to, so minus half mu naught HD dot M into dV, so into volume. So HD, let's say if I say it's a sphere, so HD is will be equal to minus 1/3 of M, and so the energy, magnetostatic energy, will be equal to, so 1/6 mu naught uh, M square uh, into the volume. So this is multiplied by volume. So I'll just hold a minute. I have to take this call. Is it still visible to you? Oh, sorry. Uh, yeah. So can you hear me now?
Yes, sir.
Yeah. Okay. So let's go back. So we have a magnetostatic energy which is given by this equation, okay? And like if we take a sphere, so for sphere of radius r, so the volume is of course 4 by 3 pi r cube. So my EMS will be equal to 1 by 6 mu naught m square 4 by 3 pi r cube, which will be equal to uh, 2 by 9 mu naught pi r cube into m square. Okay, so this is what I will get the magnetostatic energy for a sphere. But what we want to calculate is, so this is, let's say, the magnetostatic energy of this case C. Okay, but now we want to calculate the magnetostatic the energy, total energy in case B. Okay, so now we have to introduce a domain wall energy as well. The magnetostatic energy will be different now. So now we have two different domains actually. So one domain which is pointing up and another which is pointing down. So we have one domain which is pointing up and one domain pointing down. So therefore the HD will be different here. So so let me again go back here so I can add here one more. So now what we have is, so if I take this case, so I have magnetization pointing up and magnetization pointing down. So my uh, magnetostatic energy will be half of the previous case when there was no domain. Okay, because I have divided into four two equal domains. So which will be equal to 2 by 9 into mu naught pi m square r cube. Okay, so which will be equal to 1 by 9 mu naught pi m square r cube. But I have introduced another domain wall here, so which will cost extra energy, and this energy will be so typically this domain wall energy. So one can do like a comprehensive calculation, like a detailed calculation of that. But typically, this domain wall energy, you can say it like, so we have a domain wall which is uh, so sigma dw I call, and then I put a 180-degree here because this domain wall is a 180-degree domain wall. So normally it is called as a 180-degree domain wall. Why? Because the magnetization is rotated by 180-degree across this domain wall. So it is, let's say, pointing, so 0 and 180-degree in the other domain. So therefore it is called as a 180-degree domain wall. So this is the energy, extra energy that will be uh, that will cost to create these domains. So now, so the question is which one will be stable? So we can write, let's say, this case B. So this is the figure B which was here. Okay. So we can say our E B will be equal to 1 by 9 mu naught pi m square r cube plus sigma tw 180-degree. Right? This is what the domain. Uh, oh yeah. So this is typically this domain wall energy is expressed in energy per unit area. So we have to multiply to get the actual energy. So we have to multiply, like in the previous case we multiplied by volume. So here we have to multiply by the area, which will be equal to pi r square. So this, so if you take a cross section here, this cross section, so this is nothing but a circular cross section, and basically a circle, and therefore the energy that is associated with this domain wall will be, or the surface area here is a circle, surface area of a circle, so you multiply that to get the actual energy. So this is your energy per unit area. So this is your EP. Now if you want to calculate or know which one is your stable configuration, or if you say my single domain is a stable configuration, in that case EA should be, or EC should be equal to EB, right? So in that case, the single domain ferromagnetic particle will be energetically favorable. So, and one, when this will happen, so when, so if you look at the energies, one is the magnetostatic energy, R cube should be equal to 1 by 9 mu naught pi m square R cube plus sigma 180-degree domain wall into pi r square. And so if I take this out, so I have 1 pi m square r cube, which will be less than sigma domain wall 180 degree pi r square. And so I can write down that this r will be, if r, this radius of this ferromagnetic particle, if it is less than this value, so pi is also cancelled out, with then 9 will be on this side, mu naught m square. Okay, so if my radius of the ferromagnetic particle is less than this value, so I will have, so the energy of a single domain particle will be favorable, because uh, and because creating a domain or domain wall will cost a lot more energy. Okay, so similarly you can also do the same thing for case A as well, and we can also calculate a critical radius, for which we can call it a critical radius, for which you will have a single domain particle. Okay, so this normally happens. So if you substitute like these values, so typically this radius will come to be few nanometer. Of course, it depends again on materials. So for different materials, this critical radius can be different. So it can be few nanometer, and it can go to even like few hundred nanometer as well. Okay, so it is not like a fixed number like 20 nanometer or 30 nanometer, and below that all ferromagnetic particle will be in a single domain state. So it very much depends on the material. Okay. So this figure here shows basically, so the whole exercise that we did tells you that we can have a single domain particle. Okay, and this is possible energetically as well, when we look at the compare the energies of single domain state and a multi domain state. And it clearly happens for certain value of a certain size of the particle. And uh, and that actually has also been observed experimentally as well. I mean, what we did is a simple theoretical back of a paper calculation kind of thing. But here in this picture, you can see, so what is plotted here is a coercivity. So in in hysteresis, so typically you describe it with a coercivity with saturation, magnetization, remanence. Okay, so the coercivity here, so is plotted as a function of particle size. So what happens is, so as you decrease the particle size, so your coercivity is increasing, right? So it is increasing, and then under a critical dimension, or let's say the particle size dc, so there is a transition from a multi-domain to a single domain state. And again, once the transition happens, this coercivity, as you decrease the size further, so the coercivity is decreasing, right? And then for very small particle, it goes to the super paramagnetic region. Okay, so it is not anymore in a, of course it is always in a single domain state. Okay, it is still single domain, but it goes to something called a super paramagnetic region, where your coercivity is actually zero. So the coercivity vanishes, and this is what the hysteresis is plotted here on the right hand side. So in the blue region, you have a big, larger hysteresis. Why? Because you have larger coercivity is large. So therefore, the hysteresis loop is bigger or larger. And the green one shows basically that you have coercivity, but you have hysteresis, but coercivity is small. And then this red curve shows that that although the particle is a ferromagnetic, okay, so it is still in a single domain state, but it does not show any coercivity. So what this superparamagnetism represents, so that it shows it has a very high saturation magnetization. So 1000, it can be 1000 or even 5000 mu Bohr, because you almost have like, so when you take these two or like few nanometer of clusters, okay, so typically 10 nanometer clusters will maybe have 1000 atoms or 2000 atoms, right? And like if each atom has, even if you say each atom is contributing or having a 1 mu Bohr of magnetic moment, and you are taking, let's say, 2000 atoms, so the total magnetization will be, you just add them up, so you get 2000 mu Bohr. So compared to any other, like a typical magnetic moment, atomic magnetic moment, so the super paramagnetic particle has a huge magnetization. And what additionally happens, so why do you have this coercivity that goes to zero, even if you have a single domain state? So there is something which is known as a thermal fluctuations of super spins that happens. Okay, so this super spins, this single domain ferromagnetic particle, they, the magnetization, although it is huge, but there will be a fluctuation induced by temperature. So even at room temperature, it fluctuates, and since it is fluctuating, so you can say it is very similar to a behavior like a paramagnet. Okay.
Hello, sir.
Yes.
Sir, for the larger value of particle size, it is also going down. Then the superparamagnetism is also follow for larger value of particle size.
No, again, say the question.
Sir, for the larger value of particle size, the curve is also going down. Then the superparamagnetism is also follow for the larger value of particle size.
Oh, no, no, no. So for large size, yeah, you have like a big region for single domain size, right? Okay, so the single domain size you can get, let's say, maybe at 50 nanometer or maybe 100 nanometer. But the super paramagnetic region will appear actually at a small, even smaller value of your dimension, so few nanometer only, so maybe 20 or so it may not go. Again, it depends on the, on what kind of material we are talking about. Okay, whether, so for iron, it is like around 30 to 35 nanometer. Uh, I mean, if you take some other alloys or something, it can be higher. Okay, so this transition from a, a ferromagnetic to a super paramagnetic region can happen at different dimensions or different sizes for different materials. But typically, the super paramagnetism is how you know that you have a super paramagnetism, that when you measure this M versus H at room temperature, let's say, so although you will not see any hysteresis, but you will always have a very high saturation magnetization, MS. So coercivity will be, of course, zero, but you have a very high saturation magnetization. And this thermal fluctuation will be induced. So we will see how this thermal fluctuation will be there in just a couple of slides. Now, if you have this thermal fluctuations, uh, so why this name paramagnetism? Because in paramagnets, what you have is you have this magnetic moments which are fluctuating due to your thermal energy, and therefore the randomization happens, and you have a zero magnetization, right? So in paramagnets, so it, the net magnetization is zero. So if you take an ensemble of paramagnets, okay, or this your spins or your atomic moments, they are thermally fluctuating, and therefore they behave like a, so they're called paramagnets, right? And therefore this name paramagnet is introduced here, but it is not some ordinary paramagnetism. but it is like a super paramagnetism because it is happening in large clusters, so large particles where the magnetization is quite high. So the magnetic moment in case of paramagnet, which is fluctuating, is like a few mu bar, like atomic magnetic moment. But in this case, the fluctuating, the magnetization, even if it is like 1,000 mu bar or 2,000 mu bar, still it is thermally fluctuating, and that is why it is called as super paramagnetism. Yeah, so here in this picture, you see here that there is a critical radius that exists below which you will have, it is still a ferromagnetic particle, but there is a thermal fluctuation. Okay, and that's why it is called a super paramagnetism. So you start with a big bulk material where you have lots of domains, and as you decrease the size, so of course the number of domains will decrease, and then at a critical size, so you go to a single domain state. But in single domain state doesn't mean there will be fluctuation, so it can be a stable ferromagnetic body with a single domain. But once you reach another critical radius or critical dimension, so the ferromagnetic single domain particle will start fluctuating, and the coercivity will be zero, and it behaves like a super paramagnet. So these are some images. I think you can have a look. So different shapes, you can have different shapes, different sizes, uh, in different dimensions. This ferromagnetic. So this is a magnetite nanocrystal. So one of the most studied ferromagnets. Yeah, super paramagnetic system so far. Yeah, these are some just few images I wanted to show you so that you have a idea, like this can happen at different length scales. Okay, so the this nanocrystals can have different sizes, they can have different shapes, this magnetic clusters. This is how they look like under like electron microscope, or if you look at yeah, TEM or SEM, for example. But what you see here is these are your high resolution TEM images, but they are highly crystalline. Okay, so these actually show that this this individual particle is really crystalline in nature. Okay, and they are actually in a single domain state. So to understand this single domain uh, particles, so there are different models which actually exist. Uh, yeah, so one is, so so normally when we talk about ferromagnetic particle, so you can study their behavior under a magnetic field, obviously, right? So like hysteresis, and that can be understood using this Stoner-Wolfert model. So this Stoner-Wolfert model shows you the behavior of a, a ferromagnetic single domain particle due to a magnetic field. So there is another model which is called uh, yeah, this Neil Brown model. So this Neil Brown model describes the super paramagnetic behavior, this thermal. So how the um, ferromagnetic particle will behave in presence of temperature. So one model about how it behaves in a magnetic field, and this model how it behaves in temperature. So we will discuss about it detail tomorrow in the class. Yeah, so one has to calculate the energies and so on. So we'll do that tomorrow in the class. Yeah, so there is a question from Ronak that for which shape value n is minimum. No, there is not like a minimum. If I go back, uh, yeah. So this value of n, sorry, the value of n is different for different geometries. So for sphere, because the distribution is isotropic, so we said this n will be one third. So if I take, for example, an ellipsoid, or let's say if I take a cylinder, for example, that is even, yeah, easier. So if I take a cylinder, so in that case, so this is my cylinder. So always another thing with this demagnetizing field is, I mean, this gives rise to a anisotropy, a magnetic anisotropy. Okay, so what does that mean? That means the magnetization would prefer to lie along a direction in which this demagnetizing field is minimum. So that means, let's say if I take, let's say, something, a block like this. Okay, I can have magnetization like this, I can have magnetization like this. Okay, now which one would be a preferred orientation for magnetization? So that is determined by this hd, value of hd. So in this case, the vector hd is in this direction because m is like this. In this case, your hd, your demagnetizing field, is in this direction. So now as soon as you have this magnetic field hd, so it will create some magnetic poles on the surface. Okay, so in this here also you'll have magnetic poles. And therefore, once you have these magnetic poles, so always in nature, what is they want is that these magnetic poles should be as far apart as they are. Okay, so that way they can reduce this hd field. So this demagnetizing field will be reduced in that case if the poles are far apart. And that's why typically, and that is what this anisotropy means. So typically, if I take such a geometric shape, okay, like a rectangle or like a bar, the magnetization preferentially will stay along this long axis rather than along the short axis. Even if I take, for example, like a ellipsoidal shape, okay, so I will have the same kind of, so I will have surface magnetic poles here, and in this case I will have here. And now in this case, this hd field will be much higher, okay, because the poles are closer, and therefore the hd value of hd will be less in this case, and that gives rise to anisotropy. And if you take an ellipsoidal shape, ferromagnet, so the magnetization typically will prefer to lie along the long axis of the ellipsoid. Okay, and similarly in case of cylinder, so this, the m would also prefer to lie along this axis rather than the radial direction, because your hd will be minimum in this orientation. And then this value of n here will be 1 along the cylinder axis, and it will be, oh sorry, n will be 0 along the cylinder axis, and it will be equal to 1 along the radial direction. So along the radial direction, so n will be 0 along the cylinder axis. So this n, value of n, can be different for different geometries. Okay, so preferably, if you want to minimize the effect of demagnetizing field, so you take a sphere. Okay, so because then n is kind of isotropic, or the sphere is like an isotropic structure. Okay, so you n will be, yeah, you can say n will be minimum in that case.
Okay, sir. Thank you.
Yeah. Okay. So even like if you take thin film, that is also different. Okay. So if I take a thin film, for example, Let me choose. So if I take a thin film like this, so what will be the, so this is like, you can say it is determined by the shape. So this is an anisotropy, which is additional anisotropy that is introduced due to the shape of the geometry. So again, in most of the thin films, you will find that magnetization lies in the plane of the film rather than perpendicular to the film, and this is exactly due to, in order to reduce this HD field. So in this case, n will be again will be 0 along the film plane, and n will be equal to 1 perpendicular to the plane. Okay, but normally many ferromagnetic material do not have really this clear shapes, so they can have very arbitrary shapes. Okay, and very difficult to calculate this HD is actually. That is again lot of exercise to do that, to calculate HD. Okay. Okay.
Yes,
Any
yes.
other question? So we'll continue with the discussion tomorrow with this super paramagnetism. I mean, right now in the first fractal, basically we will be discussing different kinds of nanoparticles, nanoclusters. Okay, so we'll also discuss about semiconductor nanoclusters. So we'll talk about their quantum dots. Then we will talk about discuss about their this. This 2D structures, okay, and then we will also discuss about this carbon nanostructures, and then in the fractal 2 and 3 we will only discuss about different applications of that, okay.